J1, 2, 3 are a set of generators for the Lie algebra SO3. So they satisfy these commutation relations here. And if you think of these as matrices, then we can define this object here, which is not in the Lie algebra, which is just the sum of J1 squared, J2 squared, 2 squared, and J3 squared. And we want to study the matrix commutator of this J squared with any of the generators. And we want to do this without reference to what these matrices really look like. We only want to use this relation here. So just if you have a bunch of matrices that satisfy this, can we already conclude what this commutator here is. So what's this? By definition, we have here the sum over J, let's say, and then we have the commutator of Jj squared and Jk. And now this, let's spell this out. This is Jj squared Jk minus Jk Jj squared. Okay, but this we can write creating one of these commutators by first writing a Jj here and then say the second Jj and Jk. And now it would be nice to have a minus Jk Jj so that this becomes a commutator. But this last term here, it's not here. So we subtract it and then we add it again. So when we add it again, we have to add Jj, Jk, Jj, and then there's the last term, which was Jk, Jj squared, so I write it as Jj, Jj. And this last term is also a commutator. Here we have Jj, Jk, and here we have Jk, Jj, the minus sign, and just a final Jj. So we can really write this as sum over J, Jj, commutator of Jk with Jj with Jk, plus commutator of Jj with Jk times Jj. Good, and now we can use the Lie algebra relations here, which means we get a double sum, let's say J and L, and now we have an epsilon JKL, and here we have the JJ, and from this one here we get the epsilon and the JL and actually this I, which I almost forgot. So there is an I here and a JL here. And similarly for the second term, it's an epsilon JKL, but this time it's JL JJ, the other order. Good. What do we do with this one? Well, let's rename the indices in the second term. Let's just call this L here J, and let's call the JL. So here's an L and here's a J. And now we have Jj times JL in both terms, and the sum of two totally antisymmetric epsilons. So we have I times sum over J and L, epsilon JKL plus epsilon LKJ, JJ, JL. But we see that we get the second epsilon by swapping two indices in the first epsilon. So the second term is minus the first one, which means this is 0, and the whole thing vanishes as claimed.